So again, I said this before, I'll say it again. This is a challenging topic. A lot of people take some time before they really get it. And so, that might be because I don't explain it very well today, but I think it's also just a tricky topic that takes a while to learn, and you have to practice it, And so I just want you to understand that if you walk out of here going, I don't know what the hell he was talking about today, that's probably okay. You're probably not the only person who feels that way. There is book material on this starting in chapter 7, so that's a good secondary resource after class today to look at. The tricky thing about recursion, one of the reasons that it's hard to learn is that in order to understand recursion, you must first understand recursion. You'll get that later. Okay, so what's recursion? Well, recursion is when you define an operation in terms of itself. And to be more specific, what I mean is that you can describe a way of solving a problem in terms of solving a smaller occurrence of that same problem. What does that mean? Like, what's an example of that? Well, imagine the task of looking up the definition of a word in a dictionary. Not even a computer, just real life. You have a dictionary. It's one of those books I talked about that old people read, You want to look up a word. So you open the dictionary to the page where that word is at, and you find the entry for the word, and you read all of the, you read the definition to yourself, and you say, oh, okay, that's the definition of the word. But what if, have you ever had this happen? What if some of the words in the definition are words that you don't know what those mean either? You got to look those words up now, right? So you turn to the page of those words, and what if the definition of those words has some other words that you don't know what they mean? You have to, so if you were going to describe to somebody how to look up the definition of a word, part of your description of how to do that involves looking up words, looking up other words. So you're describing the task in terms of itself. And you might say, well, what if I get stuck? Looking up word A sends me to look up word B, which sends me to look up word C. Will that ever end? Well, I think the idea is eventually the process will end, right? When will it end? When will you stop having to jump to further words? Well, right, when you know all of the words that are in the definition, you don't need to look any of them up anymore. You won't have to jump around anymore, right? But anyway, my point is just you're describing the task in terms of itself. You're describing looking up words in the dictionary in terms of looking up words in the dictionary. And so this is something you could do in code. It's called recursive programming. And we're going to learn a lot about it in this class. It's going to be a big part of our course material. And one of the reasons we're going to spend so much time on it is that it's extremely powerful for solving certain kinds of problems. There are certain examples, and we will do some of them together, where this technique will allow you to write these very short, elegant solutions that will solve the problem correctly, whereas if you didn't use this idea, it would lead to a much longer, messier solution, etc. There are even some programming languages where this is the primary method of all code, called functional languages, where pretty much every piece of code you write uses this idea. So you have to learn about it like in the first day of class if you want to code this way in those languages. So like I think across the pond at Berkeley, they used to learn their introductory programming in what's called a functional language called Scheme, but they've changed since then. But anyway. So here's an example from real life. What if I want to know how many people are in a given column of this classroom? So like as an example, there's a column right here next to the aisle with all of these people going back to the back. So if I want to know how many people are in that column, of course I can just sit here and count these people's heads until I reach the back, right? But I'm an old person, and so I don't have very good vision, and so I can't really see very far back. I see there's a guy wearing a Stanford shirt there with glasses, but I can't really see much past him, so I'm just not going to be able to count this all by myself. And I'm lazy and out of shape, so I'm not walking all the way back there. I refuse to do that. So maybe what I'll do is I'll ask people to help me. I'll ask the people in this column to help me figure out the answer. So of course what I'm doing is I'm trying to come to a point where we develop a recursive algorithm for solving this problem. Okay, well, if I wanted to solve this problem recursively, the idea is that I describe the task in terms of itself. So what does that mean in this context? Well, usually when you're doing recursion, you think of it as a bunch of little workers, each solving a small part of a large problem. And in this case, my workers are the people in this column right here. If each of them helped me a little bit, maybe together we could find the answer. And the idea is that they can talk to each other, but we're not going to be doing things like for loops here. Like, I'm not going to grab one of these students and say, you do a for loop all the way to the back and count your friends up. Instead, you're just going to talk to each other. So how would you do this? Well, any ideas? How could we each handle a small portion of this problem? Like, if he's going to talk to him and he's going to talk to her, and somehow they're going to send information back and forth through the column, how do you count the people in the column? Any ideas?
So maybe you ask, you keep asking until you get to the back, and then the person at the back has 0 people behind them, so they tell the person in front of them I have 0, and then the person says, well, I have 1, so I have 1.
Okay, right. So I think a good, she gave a great answer. I'll repeat what she said in a second. A good mental model is just to pretend, no offense, pretend that each of these people is a real simpleton. And they're not capable of following very complicated instructions. They're also not capable of things like counting, moving around. They're just kind of drones, kind of like those Berkeley students I mentioned earlier. Now, I know you guys are capable of much more than that, but you'll play along with me, right? Now, what she said was an interesting idea. If I ask you how many people are in this column, you're going to say, well, I don't know, it's a bunch, I can't really see. So you don't really want to do all that work all by yourself. So maybe you could just ask the guy behind you the same question. How many people are there in the column? And he doesn't know, it's a bunch, I don't know. You ask the gal behind you, how many people are in the column? And you keep asking that all the way back, and none of you knows the answer, right? So it gets all the way to the back. The gentleman in the back with dark hair gets asked the same question. How many people are in the column? And he turns around and says, I don't know, I'm going to ask the person behind me. Oh, there's no one behind me. What do you know? Let's pretend the people on the floor and standing up don't count in this exercise, right? So you in the back, you also don't know how many people are in the column, but you do know one thing that your buddies didn't know, right? And that is, there's nobody behind me, I can tell you that. So I know there's me and no one else back from me. Does that help at all? If he tells that to the person in front of him, does that help her in some way? Like, are we getting somewhere at all with this? What do we do at that point? What do you think? Yeah. Okay, so there's kind of an adding 1 plus 1 kind of aspect here. So maybe the guy in the very back says, well, there's nobody behind me, but I'm here, so there's one person that I know of, which is me. And she says, oh, okay, well, I guess now I know that there's one person behind me, and I know that I'm a person. So I know of 2 people that there are. So maybe she tells the person in front of her, well, there's 2 of us back here. If that's helpful, there you go. And then the gal in front of her says, well, okay, and I'm 1 more person, so I know there's 3 people, me and back. And then that kind of plus 1s its way back to him at the front. And when that information gets all the way back to him at the front, he knows how many people are in the column, even though he himself didn't actually count them. In fact, no one person did all of the counting. Do you understand that? Like, yes, we're kind of counting by plus 1ing around, but no one person is doing all of it. There's no counting manager in charge of all of this. There's no real for loop here. You understand? A bunch of little workers doing a small part of the job. So I know it's a little bit tedious, but I want to actually try it. So do you understand the algorithm? Ask back and pass up. So how many people are in the column? I really want you to do it. Say it. Go ahead. Thanks. There are 12 people in the column. Let's hear it for our volunteers. Nice job. I tried to give this same lecture at Cal, but I had to dismiss them after 50 minutes. They still weren't done. I'm just kidding. No, so I mean, I know that's a little bit silly, but I think the takeaway here is that they all were basically following the same instructions. The instructions are, if you ask me how many people there are, then I will try to ask the person behind me to get the answer from them. If there isn't, well, I think what the slide says, the slide phrases it in terms of how many people are behind me. But basically, the algorithm here is I'll try to ask the person behind me what the answer is. And if they have an answer how many people there are back there, then I'll tell you one more than that. If there isn't anybody behind me, I'll just tell you that it's just me. There's just one person. Now, you might say that different people were behaving in different ways. But each of the people in this column were kind of following the same instructions. They're trying to ask the person behind them. And if that fails, they fall back to saying it's just me. All of them agree on that algorithm ahead of time. And if they all follow that algorithm, then collectively we will get the right answer to the problem. So what is this? Why is this recursive? What's all that recursion stuff here? Because asking someone how many people are in the row, the way that they answered that by asking someone else how many people there were in the row. So they described their solution to the problem in terms of the same problem itself. But they passed the buck on to a different person. So that's kind of the idea here. Looking up the word, and then looking up the next word, and then looking up the next word in the dictionary. Same idea. OK, so if you're going to write programs that are recursive, here's what you do. You can write functions that call themselves. And typically, the code of these functions has an if-else statement that divides the behavior into two cases. One of those cases is called the base case. A base case is a simple problem that the function can solve right away with no complications and no help. So in our example of people in the column, the basic case is there's nobody behind me, so I guess there's just one of me here. OK? The recursive case is the second option. The recursive case is, well, I'm not in that basic case. I'm not the last one in the column, so I need help. If you need help, you end up asking some other person to help you solve the overall problem. OK? And like I said, the key concept here is each person in my example does a little bit of the work. And collectively, that adds up to do all of the work. And any problem that I give you, if I say I want you to solve this problem recursively, you start thinking, well, how is this problem similar to itself? How is this problem solvable by smaller copies of the same problem? OK, let's do a code example. Let's try to bring this to C++ land. Here is a function that you pass it an integer parameter, and it will print that many stars on the screen, that many asterisk characters. So this is a very simple function, and it just uses a for loop. And there's no particular need to use recursion here. But I just want to show you, just in terms of discussing what recursion is and how it behaves, I'm going to use this as our first example, even though the one I already have here with a for loop is fine. So let's rewrite this function recursively. And when I say that, what I want to do is I don't want any for loops in it. I want to write the code with no loops. So how do I do that? Well, let me go to Qt Creator for a second. I believe I have a project set up here. So if I want to write void print stars that takes int n, the current version of the code does this for loop. I'm not allowed to have the for loop anymore. I told you that recursive code often has this base case and this recursive case. So usually the structure of a recursive function looks something like this. If something, maybe I'll just put a question mark here. If something, then we're in the base case. And that's easy to solve. And we just do it ourselves, you might say. And otherwise, if the if statement isn't true, then we are in what's called the recursive case. And that one's hard to solve. And we will ask for help by making calls to ourselves, to our own function. OK, so let me ask you this. If I was asking you to print stars, and you're not allowed to use loops, so like I say print 87 stars, and you have to somehow 87 times call the print a star operation. We have to try to figure out what's an easy number of stars to print versus what's a hard number of stars to print. What is an easy number of stars to print? 1 star. Without a loop, it's pretty easy to print 1 star, right? So how about if I said if n is 1, then I'll just do cout star. There. Else, let's assume that means it's greater than 1. So, This is where I would want the for loop, but Marty said I can't have a for loop. Frickin' Marty, he's so mean. Well, then I don't know what to do now. So again, thinking of our silly example of the column, the idea here is maybe I can do a little bit of the work and then use a recursive call on my own function to do the rest of the work. So like, what does it mean to do a little bit of the work? Well, maybe I could print some of the stars myself and then leave the rest of the work for other people to do. Well, how many of the stars should I print myself? Maybe one of them? I'll print one of the stars myself, but now there's more work to be done, so how do I do that? Well, if only I had a function that I could call that would print the other 86 stars, I could just call that. That'd be great if such a function existed. I would call it like magic awesome function, and I would just tell it how many stars that were left to be printed, and maybe it would do the rest for me. Since I printed one of the stars, and the total number of stars I need to print is n, how many stars does magic awesome function need to print? N minus 1. Well, now the only problem is that this doesn't exist. I really wish there was a function that existed that would do that. Oh my god, I just thought of something really cool. What if I'm the magic awesome function? Oh my god. The power was within me all along. Okay, so what's happening here? So if I call print stars and I pass it like 5. Wait, why didn't that work? Oh, I held it wrong. I have it on a magic pen here. 5. I passed 5. Okay, n is 5. So it goes to here. Is n 1? No, 5's not 1. So it goes down here, else. C out, star. So it prints a star. Then it says, now I have to call print stars with n minus 1. n minus 1, 5 minus 1, that's 4. So that makes it call this function again, but with an n of 4, right? So again, is n 1? No, print, or so it doesn't go in the if, it goes in the else. So that prints a single star. So, okay. Then it calls print stars again with 4 minus 1 is 3. N's not 1, print a single star. Call it with n minus 1, that's 2. Do you see what I'm doing here? I mean, so now I'm down to 2. It's not 1, so print a single star. Then call it again with 2 minus 1. That's 1 if n equals 1. Ooh, I am 1 now. N is 1. So I'll go in here and I'll just do this case. So I'll print a star, but I didn't make any more calls there, so we're done. It stops. And so I printed 5 stars without a for loop. Does that sort of make sense so far? I mean, this does work. I mean, I guess if you don't trust me, I can run it real quickly here. Where's main? Don't look at that stuff yet. We'll write that later. Let's do print stars, 5 stars, and then let's do, we need a endl, see out, endl, and then let's print stars 17, and then another endl. Because, yeah, okay, compile, run. Oops, it's still compiling. So, yeah, that season premiere was pretty awesome. Game of Thrones. Not going to spoil it, don't worry. But they're all on BitTorrent if you want them. 5 stars there, 17 stars there. So our print stars function is working. I guess definitely some people look at this code and they go, well, that looks weird. That doesn't make sense. That seems like that shouldn't be legal, you know, but it does totally work. Do you guys have any questions so far just about what it's doing or the mechanics of what's going on here? Yeah.
I was wondering, since we see out a star in either case, would it be like better style to do see out star and then like if n is not equal to 1?
That's a great question. She said, well, aren't we doing this see out of a star both times? So, like, can't we just, like, move this out there and then just not do it there? Yeah, that would also be totally fine. I wrote it the way that I did because we were just sort of organically writing it as we went along. And now that we're done writing it, I think we want to kind of clean it up a little bit. But I guess the reason I had it the way I had it for the moment was, like, I think it's OK to think of the 2 cases as being totally separate. Like, what do I want to do in these 2 cases? That's a good way to start. And then when you're done, if there's similarities, you can sort of pull those back out. I think it's very difficult when you first look at the problem to say, oh, I can see that these two lines are always going to be there. And so that would be more of a now, later in this process thing to pull that and clean that up. And I'm going to leave it this way for just a second, but I want to get to that in a second. Yeah, was that your question too? OK. Yeah, in the back.
Why do you need a base case?
Why do I need a base case? That's a great question. It seems like really, let me just comment out that and comment out that, right? So now it's always going to just print a star and call print stars n minus 1, right? What will that do? So if I call it with 5, it'll print 1 and then call it with 4. It'll print 1 and then call it with 3. Print 1, call it with 2. Print 1, call it with 1. Print 1, call it with 0. Print 1, call it with -1. Print 1, call it with -2. Print 1, call it with -3. We will produce what's called an infinite recursion, because it will never stop calling itself. And so that will actually lead, when you call functions in the memory of the computer, it allocates a little bit of memory so it knows where to jump to and stuff. It's called a call stack. When your program crashes and you get the list of line numbers, that's the call stack dumping out. The call stack has a limited size that it can reach. And if you exceed that size, you get a stack overflow. You might have heard of a website called Stack Overflow. They're making fun of this bug, this crash, basically. The program will crash at that point. So we have to have this base case so that the repetition will stop at some point. Just in the same way, it's almost like having a while true loop if you don't have a base case. You just never stop calling yourself. Another question, yeah?
Instead of writing the base case, could you not just say if and not equal 1?
Right, so let me refactor a little bit here. So I'm going to put back the if-else. Now, let's combine what you were saying and what she said, which is like this C out of a star we always do. So a little bit like that. And then you're saying, well, if n equals 1, there's nothing to do. So if you have an empty case like that, you don't need to write it this way. You could just say if n is greater than 1, call myself again. Right? So this would, I think, also work, right? The reason I didn't write it this way initially was because I think the pattern of attacking a lot of these types of problems is to think of it as two cases, a base case and a recursive case. And an if-else usually represents the split between those two cases. Once you actually write the code out and you sort of step back from it, you start noticing this kind of stuff. Wait, maybe I can simplify this a little bit. But I think the general pattern of if, base case, else, recursive case, that will work for pretty much any type of tricky recursion problem that you're solving. And some of them, like this one, you can clean up into a if without an else or something like that. OK? This function doesn't do the right thing if you pass it a negative n, but we're just ignoring that for the moment. OK, well, let's jump back here to the slides for a second. I've got a Socrative question that I want to ask you guys now. So let's play. If you guys are on the Socrative, get your distraction devices ready. So finish. I have to grab all the logins. OK. Now let's do a quick multiple choice question. And here is the question. So here's a recursive function that I've written called mystery. And I want you to try to walk through what it does. And what do you think it does if I pass it the number 648 as a parameter? Take a look and cast your vote. Feel free to talk to your neighbor if you like. Okay, I'll give you another second or two, but go ahead and cast in your vote, and I'll show the results in just a sec. It looks like there's a pretty clear favorite, and that is answer B, which got 86% of the vote. That's good. I think that's the right answer. Let me go check. Let me go double check here. So what's really happening here? Oops, where did my slide go? Where did it go? Okay. So, yeah. Here's the slide. So mystery, when I pass it 648, so n is 648, right? N is not less than 10, so int a is n divided by 10, which is 64. B is n mod 10, which is 8. So then I call mystery on 64 plus 8. So I call mystery on 72. So I repeat, is that less than 10? No. So then I do this AB stuff again. So now A becomes n divided by 10 is 7, and mod 10 is 2. So now I call mystery on 7 plus 2. I call mystery on 9. If n is less than 10, I return n. So the answer that comes out of here is 9. Okay? So that's kind of our first recursion mystery problem that we'll do. Let's look at a few more examples of coding with recursion. So here is a POW function. Raise a base to an exponent. Do exponentiation on integers. And so one way you could do that is just using a for loop again, right? You repeatedly take the base times itself, and times the base until you get the desired power. For 1 to exp, take result times base. You guys know I'm all about that base, right? So, yeah. Anyway, let's try to write this recursively. Recursively, no loops. So if we're going to write power, let's find that. I think I've already declared a prototype, int power. So I'll jump in there. And I did the hard part. I wrote the heading for you. So again, when we do recursion, the general strategy is we say if something, else something. And usually the if here is like what's an easy case and what's a hard case. Like easy means base case and hard means recursive case, right? So in terms of powers, math, exponentiation, like base to the exponent, what's an easy one that we wouldn't need any looping or fancy stuff to do? To the 1 power. So if I'm raising the base to the 1 power, that just means 10 to the first or 3 to the first is just the number itself, right? So I return the base itself. That's pretty easy. Okay, so harder case would be an exponent that's bigger than 1, right? If the exponent is bigger than 1, so that means I'm trying to do something like 3 to the 7th or something. 3 to the 7th. Well, is there any way that I could break off a small portion of this computation and do that part myself and have recursion compute the rest of the computation for me? A useful mental model here, remember how I talked about like, dang, if I had an awesome function or whatever I called it, and the awesome function, like kind of the way you think of this awesome function is, what if I had a function that could compute powers for me? And the only constraint was I'm not allowed to pass it the same base and exponent that I was given. I have to chip it away a little bit. But then as long as I chip it away a little bit, it can do bases and exponents on the rest of it for me. What part of it could I chip away? And what part of it would they do? Like any ideas here? What do you think, sir?
Be base equals base squared or base times base.
Base times base? OK, so I could do base times base once. And then I could leave the rest for my awesome function. Well, I guess the thing you have to be careful about is like if you do base times base and then you do base times base, base times base, you're going to get to the 2nd to the 4th to the 8th to the 16th. And we want to be able to compute odd powers too, right? So I think this is on the right track. Like we want to sort of multiply times the base once and leave the rest for magical recursion to help with. But I might phrase it like a little differently. Like, can somebody rephrase a little bit? What do you say?
Return base times power base x minus 1.
Right. So I'm going to call myself, and I'm going to pass the same base. I'm just going to pass the exponent minus 1. Because we all know that 3 to the 7th is equal to 3 to the 6th times 3 to the 1, right? That's true. And our base case is capable of doing the part on the right. To anything to the 1, we can handle, right? Ourselves, using that easy part, that base case part. This 3 to the 6th part is the tricky part, and that's where I need to use my awesome function. And I'm allowed to use my awesome function as long as I chipped away a little bit of the values so that what I passed to him is a little different than what was passed to me. And that's the case here because I chipped away a little bit of that exponent down. And what you have to convince yourself of is the progression of those calls will eventually reach my base case. Is that true? Well, if the exponent is greater than 1 and I keep chipping away minus 1s from it, then eventually won't it get to 1? So we will get to the base case eventually, you understand? So that's kind of the way you're gluing these calls together. And again, it's not the awesome function, it's my own function times power. Right, so I think I have some calls in main here that test this thing. Let's try it. What do I got? 3 to the 4th, 81, I think. 4 to the 3rd, 64. 2 to the 10th, 1024. 5 to the 3rd, 125. 0 to the 5th is 0. OK. I think one thing that's happening here is there are more calls that I'm not seeing. Do you see 0 to the 5th is on line 51 there, but there's more calls, and I'm not seeing any of the results of the further calls? Do you know what's happening? I mean, it seemed like the program got stuck or something. Yes?
Do you have to have the base case of the exponent is 0?
Exponent of 0. We didn't think of that. So, OK, let me go back to the power function that we were writing. Down here, so base case of 1 is easy. We could also add in another one. Wait, what happened? Else, we could add a 0. If the exponent is 0, that's also an easy case. Anything to the 0 is 1, right? So now we have 3 branches in our code. If it's 0, return 1. If it's 1, return base. Otherwise, return this. This will solve that bug. My claim is that we have unnecessary code here. And it might be non-obvious what I mean by that. We have 3 cases. I claim we can simply delete one of them, and the code will still work. Do you know what I'm getting at? Which case is not necessary? What do you think? The x equals 1 case. But it seemed like that was a really important case that we wrote. Why can I just get rid of that? I mean, what makes you think that it will still work if I delete that? Just go ahead. Yeah.
So if I had x equals 1, then I would be returning base times power 0, which is just 1 by that x equals 0 case, so I'm returning base anyway.
OK, so let's assume I'm taking 6 to the 1th power, so it should return 6, right? So the x is not 0, so it's going into the else. And so that'll return the base of 6 times power of 6 comma 0, right? And what's power of 6 comma 0? That's 1. So it'll do 6 times 1. So 6 times 1 is 6. It's going to get the right answer. So this code still works even after I deleted that middle case. And so I thought that's really interesting because at first we thought we needed 2 base cases, but what we really found was that one of the base cases was more basier than the other one. And it sort of was enough to eat up the other base case. And the code we had before is more like what new programmers write. They have unnecessary cases that actually, if they thought about it for a second, they don't need. It's just kind of interesting aspect of recursive code. You have a question? Yeah?
Just maybe not related, but is it in general good practice to do calculations on the return line?
Oh, like return base times power? Yeah, that's fine. You could say, something equals power and then return that times base. You could do that too. That would be fine.
But it's not different.
No, the computation will be the same, and it doesn't really change the memory or the speed or something like that. So this version of the code still works. And now if I go back to main where I was testing this thing, then I think now all of the cases here in main will run. So yeah, I've got 5 to the 0 is properly giving me 1. 1 to the 8 is 1. 1 to the 4 is 1. Negative 4 to the 0 is 1. I think that's right. Okay, good. So that's pretty much a working power function for now. Some people ask about efficiency. They say, like, well, if I write a power function like this, if it has to call the function itself over and over, is that slow? Is that going to waste a lot of the time for the computer or the memory of the computer? Recursion is a little bit slower than loops. But there's two things I'll say. One is, it's not that much slower. You probably don't need to worry about it. And two is, that's very language specific. Some languages are heavily optimized so the recursion is super duper fast. And so in general, it's not true to say that one of these ways is faster or slower than the other. Really what you do is you write the way that makes the most sense for the problem that you're working on. You don't always use recursion. You don't always use loops. They're both useful in certain situations. So, okay. I wanted to just point out what it's doing. When it's making these calls, what's really happening is, I call it with 5 to the third. So it creates some memory for that function call. And so that function call's running, and it gets to this bold line. It says base times power of base to the exponent minus 1. So this call to the function halts. Now, I think what a lot of you guys are doing kind of mentally when you're tracing through this code is you're assuming that means I jump back to the top of the function, right? I jump back to the top. But jump is not the right mental model. It works for some of the simple problems we've been doing so far. But really, that's not what it is. Really, this function invokes another copy of itself. So if you want to look at a picture of that, it's like I stack up another copy of the entire function. And now that second copy starts running with a base of 5 and a power of 2. It gets to the bolded line. It says, oh, I need to make a function call to figure out the result here. So it pauses there. We make another copy of the same function. The third copy starts running with a result, with a base of 5 and exponent of 1. This is a previous version of the code where the base case was 1, so work with me on that. So this one hits the if, and it says return base, return 5. So the result of this function gets returned. Where does it go back to? All the way out to C out? No, it goes back to the previous call. This guy made the call to this guy, and he's waiting for his result to come back. And he's dependent on his result to compute his result. Do you know what I'm saying? So like this guy's waiting for this. This guy's done. I'm returning my base of 5. Where does that go back to? That goes back to right there. That 5 gets like pasted right there. And now this guy computes, oh, I need to take 5 times that 5 that came back to me. So now he's ready to return a 25, which gets sent back to here. And that 25 gets multiplied by 5. And that gets sent back to run or main or C out or whoever's calling that. Yeah, in the back.
Break the recursion.
Oh, does passing by reference? You mean
sorry,
break the recursion?
recursion.
So it's interesting to think about reference parameters mixed with recursion. It does basically mess up what I'm describing here, because the model I was showing was that each function had totally separate copies of those variables. And if you share by reference, then they're not going to be separate. But I think in most of our examples, we will be passing by value and not by reference. Sometimes we have a shared piece of data that they all want to look at, and we'll pass it by reference on purpose. But most of these examples, it's important that the exponent is different on each call. So I don't want them to like share a single exponent between all of them. Okay? So anyway, this model of like stacking up index cards or something is a way that a lot of people talk about recursion. Okay, so what is this? This is that example from the Socratic question. I'll skip that. So that whole business about sometimes you can find a more basic base case, I like to call that recursion zen. Once you become truly enlightened about recursion, you say, oh, I can think of an even more basic case than this. You know, it's like if you think you're carbon neutral and then you realize, oh, you can actually save even more carbon than that. You know, you like reach this really enlightened state and whatever people do. So 0 base case is better than 1 base case for this example. There's a lot of examples like that that we'll see as we go along. One thing I wanted to mention was our version of POW. It doesn't work if you pass it a negative exponent, because we assume the exponent isn't negative. Our code works great as long as the exponent is 0 or more. So what do? Well, if they pass you a negative number, that's a bad thing. So one thing you can do is write a comment at the top of your function and say, hey, don't pass me negative numbers. And that's fine. That's a good thing. Documenting things like that is called documenting your preconditions. You might have heard that term in 106A maybe. So that would be a good thing to write here if we had this function. But they can still do it. They could ignore our comment and pass us a negative number. So now we're getting into the issue of a misbehaving client. We've written the POW function, and the people who call it might not be ourselves. And that code that's calling the function is the client code. Maybe that code is not behaving itself. What do you do if your client code is misbehaving? Well, you could print them a message and say, hey, stupid, you're not supposed to call me that way. But the way that we usually deal with these things is by what we call throwing an exception. You might have seen this. You might have seen a little bit of talk about exceptions in 106A. Exceptions are like errors that you use to crash the program. And you guys probably don't like errors. You probably think I should avoid errors at all costs in my program. But if you're writing a library or something, you sometimes want to intentionally crash the program to let the user of your function know that they didn't use it properly. So a pretty classic thing that you do in a function like this is, you'll go down to your pow function. Where is it? Pow, 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 pow. Right here. And rather than just assuming that they pass a non-negative exponent, we'll just say, well, if the exponent is less than 0, then I will throw the exponent back at them. I don't want this freaking parameter. Just throw it back in their face, and you throw it at them. It's like people throw a shoe at a politician or something. It's like that, And this will crash the program. Kaboom. Let's see it in action. Up in the main, we have a call of 5 to the negative 3. See that? I compile and I run, and the program gets through those other calls, but then it says an int exception was thrown, negative 3, and then it gives me this stack trace. I was in the power function, and line 93 threw that error out of there. And again, we don't like our programs to crash, but this example is like the person who called that function has a bug, so we're crashing the program so they know about the bug and they can find it and fix it. So in that sense, this is meant to be a helpful crash. So this is a pretty common thing that you do when you write functions in general, and certainly recursive functions, is throw exceptions when you get bad parameters. So sometimes I'll give you on future assignments, homework 3 and above, I'll tell you to write a function that I want you to write, and I'll say, if they pass you this kind of a parameter value, throw an exception. So I'm talking about stuff like this. You can also say things like throw, hey, don't do that. I hate this exponent. Whatever. You can throw string messages out, and they can see the messages appear out on the screen as well. So you could throw different types of things at them. There you go. Anyway, I want to move on to another example. I've got a Socrative here, but I'm going to skip it for a second. I want to write a function called isPalindrome. Pass in a string, and it will return true or false if the string is the same forwards as backwards. So we talked about forwards and backwards and reversing things last week. There was a data structure that's good for that. Do you know which one I'm talking about? Stacks are good for that. We're not going to use data structures to solve this problem. We're also not going to use loops to solve this problem. But you might note that recursive function calls stack up. So they are stacky in that way. How is this problem recursive? How is it similar to itself? If I'm asking you whether a string is a palindrome, can you help answer that by knowing whether some smaller part of the string is a palindrome? Would that help you answer whether the overall string was a palindrome? What if you could know that most of it was a palindrome, and then you yourself could figure out that the rest was as well? How would you slice and dice that? What little piece would you break off, and what would you leave for recursion to do? What do you think, sir?
So it would be the first and last letter, or the second and second to last letter, and if you go chopping those down all the way and they're all the same, then you finally get to the middle, and that would be your base case. You just have to deal with the fact that sometimes it might be an odd numbered word, odd length word, or an even length word.
That sounds like a great idea. So if something, else something. So your suggestion is chop off the first and last letter. OK, fine. Char first equals S0. Char last equals s dot length minus 1. Those are the first and the last characters. So if the first and the last are the same, that tells me something. Otherwise, I'll do something else. If they're not the same, what does that mean? This is not a palindrome if the first and the last letters are not the same, right? So then I will return, oops, not comment, return false. If the first and the last letters are the same, that's a good start, but we don't know about the rest of the string, right? If only we had a magical function that would tell us whether the rest of the string was a palindrome. What if I sliced out the rest of the string s dot substring from 1 to, I'm supposed to pass the length here, s dot length minus 2. That's how many characters to pull out. That's the rest of the string. What could I return here? Call is palindrome on the rest. If my function that I'm writing works, then maybe that will do the right thing. But at some point, we have to stop this merry-go-round, right? So this is supposed to be the base case, the easy case. What strings are really easy to know if they're palindromes or not? Like short strings, like you might think if it's only 2 characters, then all I got to do is look at those 2 and see if they're the same. But you must see the light. You must be in Zen, right? 2 characters, that sounds like a lot of work. I'm too lazy for that. What's easier than 2 characters? 1 character. What's easier than 1 character? No characters. We could assume that 1 character strings and the empty string are palindromes. Why don't we say if s's length is less than 2, we know it's a palindrome. Otherwise, chop 2, compare them. If they match, compare the rest. That's an is palindrome function. I've got to stop there because we're out of time. Have a delightful day. We will do more recursion on Wednesday. See you guys later.